Let's look at Euler's method for determining an approximate solution to a differential equation. And this is tied up with everything that we've done with derivatives so far. We're going to use the tangent line approximation, and we're going to use the mean value theorem and put these all together. I guess we should throw in we're going to use the chain rule and implicit derivatives and put this all together to find out something about the solutions to a certain differential equation. Now, I'm going to cheat because I got the opportunity to take more than one semester of calculus. I know the solution to this differential equation. We don't have time in one semester to study how to do that, but it is a thing that people know how to do. And so we're going to compare the approximate solutions that Euler's method gives us with the actual genuine solutions that come from knowing the exact differential equation. After this, we're going to start worrying about other kinds of exact forms of dealing with the situation where we know the derivative. But first things first. So I've taken the liberty of writing down the equation in advance. The equation is y prime equals a fraction, well, the negative of a fraction. Top is x, bottom is y. And this is a differential equation because it involves the function y and its derivative y prime. Now, the thing is, differential equations have more than one solution, and so we're going to pick a particular case where we're going to start at the point 2, 2. So we're going to say when x is 2, y is 2. And so in doing this, you need to have a particular point. So Euler's method, this is a silly name because Euler had approximately 9 trillion methods that he invented over the course of his lifetime. But Euler's method says we're going to start at a certain point and we're going to use this to get the derivative at that point, which tells us the tangent line approximation, and we know that is close to the solution curve, so we're going to follow the tangent line approximation out for a little bit and start over. So we're going to start at some point. People use subscripts here, and so I'm going to do that as well. I've got x0, y0, and so that's some point in the plane. So for example, 2, 2. And what we know here is the slope of the tangent line. So in this case, when x is 2 and y is 2, the slope of the tangent line is minus 1. And so I'm just going to draw a little segment whose slope is minus 1. Now that should stay close to the solution curve. We know it stays close to the solution curve because it's tangent. We're going to see which way it differs in a minute or so, but that's the situation. So what we have here is we have made a change in x, and I'm just going to label these delta x, and we've made a change in y, delta y. Now in this particular case, delta x and delta y are equal because the slope was minus 1. They're equal in magnitude. Obviously the signs are different. But that takes us to a certain point. And so once we get to that point, we'll have a different value for the derivative by plugging in those coordinates, and we'll take that little step in the x direction, and the derivative will tell us the slope, so we know how far down or up to go in the y direction, and that gives us another point. And then once we start at that point, we get a different derivative, different delta y, change in y, and we get to another point. So we're going to keep delta x constant, but delta y is going to depend on the derivative at the point in question. So what I'm going to say is delta y is equal to the derivative at some point. I'm going to call this x sub I times delta x. That's just saying delta y is the rise or run when delta y is the rise when delta x is the run, and f prime at this point is the slope of the tangent. And so y sub I plus 1, the next one is y sub I plus delta y. Now, this is not something that people usually do by hand, so I uh, don't want to encourage you to do this. This is the foundation of how computers come up with approximate solutions to differential equations. And this one is pretty crude, but it gives you the basic idea. Over the years, people have developed a lot of fancier techniques for finding solutions to differential equations, which we don't have time to study in a one semester course, but they're out there. So there's the situation. So there's Euler's method. We're just using the tangent line approximation, and this is about the last of the geometry that you're going to see, because it pretty much quickly gets into numerical situations. Well, let's jump in. Now, I have gone and done the calculations in advance, and so we're going to see what comes out of it. So I'm going to use a delta x of 0.1. So every time that we move, we're going to move 0.1 to the right, 0.1 to the right, 0.1 to the right. So our x coordinates are 2, 2.1, 2.2, so forth and so on. So that's delta x. Sometimes people call that h. H is like when taking derivatives, it's the horizontal offset. And so we can use that either way. So what we're going to have is a table of x's, 2.0, 2.1, 2.2, 2.3, 2.4, and 2.5. So that's what we're given because we know the change in x. Okay. Y is, we don't know yet. We're going to try to figure out what y is, but we know the first one is 2. So that was given to us up here with the initial condition, so I can fill in here. The next thing that we're going to do with this is figure out what y prime is. We're going to take the derivative of y, and that is easier than it sounds because we have a formula for the derivative. So we're just going to take minus x over y. It's, in this case, it's not a lot of complicated algebra. And so this is more a matter of bookkeeping and organization and patience and accuracy than there's concept behind it. So I'm going to say next we're going to have y prime, and that will give us delta y. And once we have delta y, we know what the next value of y is. And so we'll just start the whole process over again at the new point at the end of that little tangent segment. And for reference, I'm going to put the actual y, not the estimated y. And I actually used Sage to figure those out because I knew a formula for the solution. And let me just write down what the actual y's are just so we know what we're getting at. So in order to 1.875, 1.778, 1.646, 1.497, and I seem to be short one. Let me see if I still have the Sage. I didn't do enough. Sorry. So we're going to just modify the Sage code so I get the one more. This cannot be very exciting to watch, but that's the way it goes. Okay, 1.323. So we're going to jump in. This is not going to be super exciting, but it's got to be done. Okay, so when x is 2 and y is 2, y prime is the negative of x over y, so y prime is just negative 1. And so delta y is 0.1, negative 0.1, because you multiply delta x by the slope. That's just the tangent line approximation. Okay, so this tells us that the next y is 0.1 less than the previous y, and so that will be 1.9. So now we have an estimate for the next value of the function. It's okay. The actual value is 1.875, and we're estimating 1.9. So we're not in left field. We're at least in the ballpark. Okay. Now it gets to be where you have to have some kind of calculating device unless you want to torture yourself. So now we're at the point 2.1, 1.9, and y prime is, you take the quotient of those and negate it. And so I've taken the liberty of doing that, and you can check me, and I got minus 1.105. So that's 2.1 over 1.9 and then negated. And then the change in y is you have to multiply that by 0.1. So the change in y is minus 0.1105. And so that's the way it goes. And that gives us a new y of 1.789. So this is a rough picture, but what we're seeing here is 2.2, and then 2.1, 1.9, and then they're getting a little bit steeper. We're going to be at 2.2, 1.789. And so we're starting to put together a solution like this. Okay. Let me just kind of fill these in lickety-split, and you can check them. I think you see how the calculation goes. I take minus x over y, and then multiply that by 0.1. 0.1 is the delta x, and that tells me what the delta y is. That's the tangent line approximation. And so the successive y's that I get are 1.667. At 2.4, the next one would be 1.529. And finally, at 2.5, we get 1.372. You can't go too far like this because, as you'll see, the errors get worse and worse and worse. So what we're doing, this will be easier when you have this scanned. We've got the actual values over here and our estimated values over here, and they're okay. But in the end, we're estimating 1.372, and it should have been 1.313. It's okay. It's that might actually be good enough to send somebody to the moon, although you probably want to be a little bit more careful about what you do there. So let's talk about some of the analytic things that make this correct, and that involves taking derivatives. So this is good practice. First of all, y prime is minus x over y. That was given. And we're in the situation here where x is positive and y is positive. So x over y is positive. So when we have x is positive and y is positive, that means that y prime is negative. So we're looking for the solutions to be decreasing. And in fact, they are. So y prime is negative. That means y is decreasing, and both our estimated and the actual solutions are decreasing functions. Every time we take a step, y goes down in value. The other thing that we can do is the concavity, and this is a little fancier. We have to use the chain rule in implicit derivatives because y is a function. So what we want to do here is we're given y prime. So to get y double prime, we just take the derivative of this, but we have to keep in mind that y is a function. So let's do that. That's a quotient. So y double prime is negative. And by the quotient rule, low d high, high d low, square the bottom. There you go. So on the bottom we have y squared. Oh, that just gives us a warm fuzzy because y squared is always positive unless it's 0. And so we don't have to worry about the bottom of this fraction as far as what the sign of the second derivative. And then when we're applying the quotient rule here, derivative of the top is minus 1 times the bottom, that's y, minus the top, the derivative is plus 1. I put the minus sign up front. The top is x, and the derivative of y is y prime. Y is a function, so the derivative of y is y prime. In ordinary circumstances, you'd be stuck here, but in fact, we have a formula for y prime, so we're going to throw that formula in and say that this is equal to the negative of well, we have y squared on the bottom, and on top we have y minus, and then we've got x times y prime, so that becomes plus x squared over y. Why is that? X times x over y is x squared over y. So x times y prime is x times the negative of x over y, so it's the negative x squared over y. So those come out to be like this. And now we say, well, wait a second. When x and y are positive, y plus x squared over y, those are all positive. And so in the situation where y is positive, then the concavity is up. So y double prime, I'm sorry, the concavity is down. If y is positive, it's the opposite sign. Y double prime is negative, so y is concave down. So you're seeing some of that here, and you're seeing some of that here because the y primes that you get are decreasing, and you see that here. It looks like they get turned down, and in fact they do. And you see that in the actual solution that the concavity is concave down. And so what we've gotten with this Eulers method is that at least qualitatively, it's giving us solutions that have the same properties. The solution curve should be decreasing and concave down. It is, in fact, a circle. And so that is exactly what a circle would be if you started at some point on the like this. So I take the circle of radius 8, that's what it happens to be, and I look at the point 2, 2, and the solution that we would be getting, I've only done part of it, so I'll kind of highlight that in red. The solution that we're getting is decreasing and concave down, and we got that by using implicit derivatives and the mean value theorem, and we also got that by looking at the numerical solutions. So we are decreasing, we are concave down, and in fact we have a circle. So we are able to approximate this circle by using this Eulers method. Eulers method is not something to be done by hand. What it really does is it's going to motivate us now to look at integration, which is our next topic, and but it does illustrate how a computing machine could, or even a person who does computing for a living, that used to be a job description in the 1930s before there were automatic machine computers, can actually compute solutions, and there are techniques for making this more accurate. So differential equations, you may not have an exact solution, but you have good ways to approximate solutions, which give you good ways to send people to the moon. So this is how they did it, and this is Eulers' method.